In this lesson, we focus on mathematics, introductory algebra, MAM2013S, a UCT approach to introductory algebra, abstract algebra. We shall look at textbook exercises and a lot more, and several group theoretic notions, abstract algebraic notions. Right, to start with, we actually look at this particular problem from the prescribed textbook, give a specific example of some group G and elements G, H in G, where we have that GH raised to the power n is not equal to G to the power n, H to the power n. Right, so obviously we actually need to think of this and look at the best way to actually tackle this particular question. Right, we can note that, for example, for n equals 2, right, any G and H with the product, for example, GH different from HG will work. For n equals to any GH with GH not equal to HG will work. Let's give an example because we need to give a specific example. For example, right, for example, let us give this particular group here. For example, in S3, we have, right, in the symmetric group on 3 symbols, we have, for example, that if we work with 1, 2, 1, 3, and you square this. And now let us first find actually the results that you get when you square this. So obviously squaring this would be the same as what? You have 1 goes to 2, and simultaneously, obviously, you have that 2 goes to 1 in this particular transposition. 1 goes to 3, and simultaneously 3 goes to 1. Now let us look at this particular presentation. 1, 2, 3, 1, 2, 3. 1 goes to 2. If you think that 2 goes to 1, 3, 3. 1 goes to 3, 3 goes to 1, 2. 1, 2, 3. Right, so if we're looking at 1, we have 1 goes to 3 and 3 goes to 3, for example. We have 2, 2 goes to 2, but 2 goes to 1. We have 3, 3 goes to 1, and 1 goes to 2. Meaning that at this point, what we can see is that if you start as follows, if you actually are able to begin as follows and realize you start with 1, right, you can see that 1 goes to 3, and 3 goes to 2, and then 2 goes back to 1. Well, this is what we observe. And this is squared. So in other words, this can be written exactly in that particular fashion. Now, let us actually perform the square on this. So if we're sort of remove, I should have removed this. And also now this equals 1, 2, 3. Right, let's have this one here. So this one says that 1 goes to 3, 3 goes to 2. You have that 3 goes to 2, and then 2 goes back to 1. And we have 3, 1, 2 still. So we begin with 1. We then attempt to square this. So 1 goes to 3, but 3 goes to 2. Okay, 1 goes to 3, but 3 goes to 2. 2 goes to 1, but 1 goes to 3. 3 goes to 2, but 2 goes to 1. Now, this is the same as 1 goes to 2, but 2 goes to 3, and then 3 goes back to 1. Right, meaning that obviously this is sort of the equivalence. We're looking at these parts now. In other words, if you have the two elements, G, H, and you multiply them, and you raise them to a power, and this is what we're getting. But let us look at what happens when we perform the following. We have the following. Now, we actually would look at, for instance, let us look at 1, 2, you square. So we square this, and we're looking at 1, 3, and you square that way. Right, so if you look at this exactly, let us reason together. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1. 1 goes to 2. According to this, 1 goes to 2. And then 2 goes back to 1. 3. 2, 1, 3 still. 1 goes to 2, but 2 goes back to 1. You have 2. 2 goes to 1, but 1 goes to 2. 3 goes to 3, 3 goes to 3. So this sort of fixes all the symbols. Now, because it fixes all the symbols, it sort of gives us the identity permutation. You can write it. One of the ways to write the identity permutation is this one. But it is very clear that even this one will yield the same thing. The identity permutation times identity permutation gives us the identity permutation. So in other words, now, 1, 2, 3, I want to demonstrate things and make sure that there's a fair level of confidence that indeed these responses have a fair degree of accuracy. So 1 goes to 3, 3 goes to 1, 2. 1 goes to 3, 3 goes to 1, 2, 1. 1 goes to 3, but 3 goes to 1, 2. 2 goes to 2, 2 goes to 2, 3. 3 goes to 1, 1 goes to 3. In which case, therefore, this gives us the identity permutation, which can also be written this way. And so obviously, this would be, in this case, the same as the cycle, this particular 2 cycle. 1, 3, and this one is the same as each one of these is the 1, 2 cycle, 1, 2 cycle. This one is the 1, 3 cycle, 1, 3 cycle, like that. But you can see that obviously, if you get the product squaring a transposition, a cycle of length 2, obviously has the tendency to yield what we call the identity permutation. What are we able to sort of what are we able to extract as a conclusion out of this? Okay, we've seen this already. What are we able to extract? Because this was just some rough work to actually justify our assertions. But what there do we have here, as a matter of fact? What then do we have here as a matter of fact? So, which means therefore this is that. And hence, right, hence it is clear that if you have the 1, 2 as our G for any GH. So for S3 we have that. For G is 1, 2, and H is 1, 3, N is 3. 1, 2, 1, 3 squared. Okay, if you square this, we have already seen that we're getting 1, 2, 3, but it is not equal to the 1, 2 squared, 1, 3 squared, because this 1, 2 squared, 1, 3 squared produces the identity permutation. Right, obviously here we're to give a specific example of some group G and elements G and H where this is the case, and we've already seen that we have given that in S3, if you take G to be 1, 2 and H to be 1, 3, excuse me, with N equals 2, right, and with N equals 2 the power, so if you square, we can see that, okay, this is the case. And we actually are able to make the observation that most certainly we can confidently say without any shadow of doubt that indeed we have the following conclusion to make, that whenever we have 1, 2, 1, 3, and you square this, it is not equal to 1, 2 squared. Okay, let's check this. Yeah, it's not equal to that. This one, 1, 3. So these are not equal to each other. Okay, yeah, but please advise us. Okay, so this is exactly the answer. Next, we move to the next question. We move to the next question. Right, we move to the next question. Right, so here is the next question. The next question is question 25 from 16. I actually took the list of the problems you brought. And now here, this one is saying, let A and B be elements in a group G. Prove that this is the case. So if you have A, B to the nth power, this is equal to AB, A minus 1 to the nth power for n in Z. Take a look at this. Take a look at exactly this in reason. And reason precisely and see what this is supposed to yield. So now, what then arises is the proof here. The couple of ways, obviously, to reason this out. And this is the solution to this. For example, we can start by saying, because n is an element of the set of integers, we can start by saying for n equals 0, for n equals 0, this is the statement. For n equals 0, this is the statement. Is a statement that A times 1, A inverse is AB, A inverse to the 0th power. And so this one would give 1 is equal to 1, which is true since both sides are the identity. Since both sides are the identity. For n bigger than 0. For n bigger than 0, we prove their statement. We prove the statement by the principle. By the principle of mathematical induction. By the principle of mathematical induction. You suppose that, right? So we suppose that, for example, a b to the power n minus 1, a minus 1 is actually equal to ab a minus 1 to the power n minus 1. Okay, you have something like this. Something like that. Something like that. Okay, but very easy. Okay, there are many ways to prove this, but we want to prove it by mathematical induction. But also this can just be, yeah, mathematical induction is a fair way to prove this, but you can also prove it using other principles. It's very easy. But yeah, we chose mathematical induction. It's popular also in your institution there. So then, for example, if you have the AB a minus 1 to the power n. So obviously now for n bigger than 0, we prove the statement by the principle of mathematical induction. Suppose that now we just reduce, because it is to the power n, so we reduce the power by 1. So that b is to the power n minus 1, but also this one is to the power n minus 1. Then, if now just increase the power by 1 more units, then it becomes AB a minus 1. Now, this is true. So now, because now if you raise this to the power n, you get this. All right, so yeah, if you raise this to the power n minus 1, a b n minus 1, which is a. Okay, so obviously you're able to see that it's gonna, this times this, so it's gonna be b to the power n this way, which is exactly what we get here on the left of the given equation. And so now we have this. Please come again.
A times A, is it not A squared?
Okay, okay. You mean here? Let me see what you're observing. Because we have with a minus 1, a to the power minus 1 times a.
Yeah, that's one. Yeah.
Yeah, and then, okay, that's fine. I'm glad that you're engaging because I wanted to write a bit more steps. So that's going to be a, b minus 1, then it's going to be 1, and then it's going to be b, a minus 1. And then now, obviously, we have a, b minus 1, b, a minus 1. And then this one is a bb. So obviously now we can use the law of indices, which applies to groups. Obviously, so now if you use the law of indices, the b to n minus 1, the b to the first power is going to be minus 1 plus 1 n minus 1. So it's going to be actually a b, and the minus 1 plus 1 is just going to give us 0. So it's going to be a b to the power n a minus 1 like that. Okay, obviously, which is exactly that. So obviously, we have just shown that if we start with the right-hand side where we have the AB times A to the minus 1 all to the nth power, then it actually produces AB to the power n A times A to the minus 1, which is exactly the left-hand side. Now, okay, this was the case for n bigger than 0. Right, but now the truth is n is an integer. If n is an integer, it has implications for both, because we have looked at the 0 case. 0 is an integer, n is an element of integers. So we looked at the fact that whenever we allow n to be 0 in the integers, then the left and the right are equal because 1 equals 1, okay? Now we look at the case where n is bigger than 0, and we can see that the left and the right are equal to each other. Now it remains to look at the fact that integers are also negative. So we look at the negative case for n negative. Finally, right, finally for n negative, let. So for n negative, we can take m to be the negative of the integer n. Moreover, using the statement, for m positive, we have, right, we have the following. So we can use this one and then say a, b, a minus 1 to the nth power. This is exactly a, b, a minus 1, m, like that. The question is this equal to this? Because we have the a, b, a minus 1, but we know that m is equal to minus n. So in other words, wherever we have the m, we can put minus n. And therefore, simultaneously, it has several implications about n being equal to minus m. So we have n equals minus m. So indeed, this is correct. And the minus m is able to reduce the power over the AB, a minus 1. So it is the minus m is the power, but now we can just factorize. Instead of having minus m, we can actually be in a position to actually write this. But this m equals minus n is necessary. Why? Because we want to make sure that we are able to use the previous case of positive n, but in a very, very cunning manner by making m equal to the negative n, where n is negative. If n is negative and you multiply it by negative n, this is therefore going to be positive, so that indeed m is a positive number. The negative does not mean it is negative at all. Okay, now what exactly is this here? This is a new ball game. Let us watch what now. If you take the negative of this, it's going to be ab minus 1, a minus 1 to the mth power, like this. Okay, if you raise this to this power, why is this the case? Why? Okay, I'm just going to put some justification on the side, because we know that if you have ab to the minus 1 according to group properties, ab is the same as b minus 1, a minus 1 according to the group properties. So this is true. Now, if these things are three symbols, because now we are dealing with two symbols, what about if you have three symbols? Like you have a, b, a minus 1, minus 1. So you can associate the things like this, so that you have a minus 1, minus 1. And then you have a, b, minus 1. You can do it step by step. Right, the a minus 1 is just a, and this one is b minus 1, a minus 1. So indeed, it is true that now the ab to the power minus 1 like that is actually the same as ab minus 1, a minus 1, like so. This is good news. What now are we able to, what can we achieve out of this? We are back to the square one case when we have a positive power. What did we say with the positive power? Right, so whenever n is positive, we said that a minus 1 n will actually just, the n is just going to sit on the b, and it's not going to affect the a, it's not going to affect the a minus 1. So it's going to just, the n is going to sit on the b this way. So this is exactly our story, and we're going to apply it here. So here it means that the m, which is the power, is not going to affect the a, but the m is going to sit on the b minus 1, and then we shall have a minus 1 there. And what is this? This is everything we ever wanted to achieve, because the minus m, according to this equation, minus m is n. So this one is going to be b to the power n, a to the power n minus 1. And this is the answer. This is the answer. So you see, we have to prove that this is the case for n in the integers, and this is exactly what we got. Any question? Okay, look, we have proven this in a series of cases. We have proven this by the principle of mathematical induction. We have proven this by the PMI, the principle of mathematical induction. And we started by looking at the fact that, okay, integers are negative, some are positive, but 0 is also an integer. So negative, like this, 0, 1, 2, 3, like that. Some are negative, some are positive, but also we have 0. So we started with the 0 case. And 0 case, replacing n by 0 produces 1 equals 1, which is true since both sides are the identity. Okay, we actually therefore we're done with the 0 case there. And then we went on to then say some integers are 1, 2, 3, the positives. So for n positive, we proved the statement by the principle of mathematical induction. We supposed that the statement is true for n less than 1, n minus 1, n that is 1 less. So because, in other words, we want to prove it for n, we can just say, okay, we subtract 1 from n, so that now we're going to have, at the power of the b, we're going to have n minus 1, but also shall have a b, a minus 1, and shall minus 1 from the n. This is sort of our induction hypothesis. Now, this here This here is our basis. Is our basis step. So after the basis step, we went on this side to establish our induction hypothesis. Induction hypothesis. Okay. All right. Induction hypothesis means that now if we say, we suppose it is true for n minus 1. We want to prove it is true for n. We separate this and it will be a b to the power a minus 1, n minus 1, and then this. We multiply everything and it becomes this. And now we then say, okay, it is true, therefore, we justified this last time. We went through the steps recipe to show, but this is true for n bigger than 0. Okay, but not all integers are positive. So some are negative. So for n negative now, let m be the negative n. Why are we writing this equation? So that we're dealing with everything positive here. Because we have established a positive case, n positive. Using the statement for m positive, because this m is positive, because n is negative, and n is negative, we multiply it by -1, making it positive, and therefore we achieved this. Think about it. Think about it. Okay, we're going to play around with these things more. We're going to play around with these things more frequently. And we're going to play around with these things more frequently. We used mathematical induction to prove this, the principle of mathematical induction. We move forward. Now, here is one result that is important. Problem 28. Problem 28. Right, so now, in problem 28, what exactly do we have? Prove the remainder of proposition 3.21. If G is a group and AB is in G, then the equation x equals B has a unique solution. So I actually have cited the proposition here from the textbook. And this problem 28 is saying prove the remainder of the proposition. If G is a group in A, B are in G, then the equation x equals B has a unique solution in G. Let's read the proposition. Let G be a group and A and B be any two elements in G. You take a group G and you take like two elements A and B that are in G, then the equations AX equals B and XA equals B have unique solutions in G. Proof. Suppose that AX is B. We must show that there exists. We must show that that such an X exists, excuse me. So we can multiply both sides of AX equals B by A to the -1, or the inverse of A, to find that we actually are able to, in other words, okay, we're going to do it here. So it's very easy, this one. We have AX equals B. And if this is the case, then we want to prove that there is a unique solution. And according to the author of this book, to prove the uniqueness, we must first do this working. So we first make X the subject. So we multiply by A minus 1 AX, and then we have A minus 1B. A minus 1 AX is just going to give us exactly X, and this one is going to be A minus 1B, which is exactly that. But to show uniqueness, suppose that X1 and X2 are both solutions of, now when I want to show uniqueness, and we suppose that there are two solutions. Okay, uniqueness suppose that, so in other words, we must show there's only one solution, but we suppose that there are two solutions, AX equals B, then AX1 is B, but also AX2 is B, so that now we can be able to get X1 equals X2. The proof for the existence and uniqueness of the solution for that is similar. Okay, so in other words, here we have proven existence. Right, so we have proven existence. In other words, we're saying the X exists. Now we actually will just comment on the uniqueness. Remember that what we are proving here, we're not proving anything new, but we are establishing okay, this is uniqueness. Oh, well, yes, it's uniqueness. Uniqueness, we suppose that there are two solutions. So now, and there are two solutions. We want to prove that. So there's a solution such that is A. Okay. The uniqueness of the solution in the event that we are dealing. Okay, this proof the reason why they're asking us is because there are two equations. Okay, we are dealing with the ax equals b. Then on the we shall do the x a equals b. So now we are looking at ax equals b. We want to prove that the solution is unique. A solution to this is x. So it's a value of x. So now it would mean, therefore, there is ax1, which equals b, which is ax2. So now we are assuming that there are two solutions. So now we suppose, right? So we suppose the existence of two solutions. Right, so we suppose there exists two solutions, x1, x2. Suppose there exist those two solutions. So now it remains for us to bring some justifications and show that x1 is equal to x2 in all these ball game. And to do this, what then do we do? We actually are able to do exactly the following. What exactly do we do here? Well, it would mean that ax1 is somehow ax2. And if this is the case, then you can write a to the power minus 1, x1 is equal to a to the power minus 1, ax2. A to the power, that is the identity of this one, which means that x1 is equal to x2. And the fact that x1 is equal to x2 obviously suggests, therefore, that the solutions are unique. So we have a unique solution, and this implies unique solution. Unique solution. Unique solution means unique solution. Unique solution X. All right. Anyhow, okay, this is exactly the existence and the uniqueness, but it is the existence for there are two solutions. Ax equals b. We must do xa equals b now. That is what we're supposed to do. We are supposed to do xa equals b. So first we shall deal with the existence. For xa equals b, dealing with the existence, that the solution exists. So we need to solve for x. Multiply by a minus 1, x equals b a minus 1. We're good. We're so good. So good. Okay, we continue. Right, so the solution exists. But now we're going to just establish the uniqueness part. We're going to establish let me do the uniqueness. Doesn't matter. You can do it here. It's not a lot of work. So establishing the uniqueness, what do we have? We suppose that, can you write down a little bit? Suppose that x1 and x2 are both solutions of ax equals b, oh no, of xa equals b. Okay, because they are just the different order. Over xa equals b. this way, right? So we suppose that there are some other solutions, x1, x2 of which, suppose x1, x2 are both solutions of the x a equals b. Right, then it means that whenever you have x1a is equal to b, but also there is another solution x2a that is also b, which means x1a is equal to x2a. x1a you multiply by a minus 1, x2a you multiply by a minus 1. Meaning, therefore, that x1 is equal to x2, and this becomes the solution. Obviously, and therefore, this means that the solution is unique. And this implies that we have a unique solution. We have a unique solution X. Right, so we're good with the unique solution X. So obviously, see, what was exercise 28? Exercise 28 was saying, okay, in the proposition 3.21, they actually have proven the ax equals b. Was supposed to just the remainder, because they said prove the remainder of proposition 3.21. If G is a group and A, B are in G, then the equation XA has a unique solution. Right, so yeah, so we're supposed to just prove the remainder. The remainder is this one, which is exactly XA equals B, has a unique solution, and the solution is in G. Has a unique solution X in G. In the same way that this one here has a unique solution X also in G. I believe it's too easy. Okay, we move to the next point. Next. Okay, next. Some of these will participate a little bit. Okay. Right, so now, so that you do not slip, prove the right and left cancellation laws for a group G. That is, show that in G, BA equals CA implies this, and this implies that for elements in the group. Let us actually reason this out together. You see, the question is, how exactly is this true? How exactly is this a true result? So let us obviously reason this very, very carefully. Let us reason this very, very carefully and think about how exactly this must be done. So, okay, it's very easy. So now, obviously, this is about, in the group, you prove that this implies this, but also this implies that. So you start with BA equals CA. So now you would have to prove that indeed this implies that. So now in this case, you are proving the right cancellation. So if this is the case, now you can actually, on the right, apply the inverse both sides. So that in this case, therefore, this will be that. You can put either identity and you can put either identity, and this means that you have that. So indeed, this is the case. In general, the reverse is true. But obviously, we're proving the right cancellation. So we're proving the right cancellation law. Simultaneously, want to prove the left cancellation law. Left cancellation, I mean right. Cancellation law. Then the left cancellation law. Okay, so it is that we're given We given, for example, AB is AC. And now on the left, we can apply the inverse. Particularly, you see, we can be more pedantic. We can be more pedantic like this. So now we use association, associativity in the group as a group property in principle. I mean, that is the level of detail we would have to show. And then at this point, AA inverse would be EB, and this one will be EC, so that B equals C. So in the same way here, you can just say, we're starting with the BA, we're starting with the CA, and then we are just doing things in order. And doing everything in order, then we come to this part, which is BAA inverse, CAA inverse, B, and this is ECE. B equals B equals C, excuse me. So obviously at this point, I mean, this should be a more organized way to do it. So we effectively then saying, if you start with the BA, applying the multiplicative inverse on both sides, and now by associativity in the group, because every group is associative. So we're using associativity here, that you can associate the A and the B were associated. We can associate different elements like that. Right, so this was too easy because we had to prove the right and left cancellation laws for a group G, that is show that in the group G, then if ever you have BA equals CA, it implies that B equals C. Whenever AB equals AC, it implies this. It implies this. Any question?
No.
Okay, good. We move forward. Sometimes you will participate a little bit. There's some questions that are coming. This one is very easy, but very interesting. Show that if A squared is the identity for all elements. Okay, this is the textbook, so it shows that E is one of those identities that is sort of popular in notation terms. Right, so show that if A squared is E for all elements A in a group G, then G must be abelian. So if A squared equals E, it implies that G is abelian. Right. Some of these, as said already, I'll give you a chance to participate and to partake to make sure that you can actually stay awake, because if there's anything that happens in class, students find themselves falling asleep sometimes. They sit there thinking, okay, I'm just listening to the teacher. Boom, they're gone in deep sleep. But this is nice, easy, and short. Let us get it right. So to do this one, you actually now would look at the proof. Suppose A, B in G. Then, so you take two elements in G. Then now we can be able to see that the identity can be seen as AB, AB. Because we need to show that if ever A squared is the identity for all the elements A in a group. So in other words, these elements A in a group, it means that every element in this group is a square as order 2. So now if in the AB we'll have order 2, so that when you have AB times AB, then you get the identity. But not only this, we are very excited to even say that even if you can actually have the following, so you can have, for instance, AB like this, and then have BA like this. So this would actually be the result, because now this one is going to have B by B, which is B squared. B squared is E. And then we have A times A, which is A squared. But also A squared is E. So indeed, also this is E, because for all the elements are in the group. So yeah, every element here at least is of order 2, at least, or at most. Okay, we have that kind of a statement. And why is this the case? This here is the case since. It is the case since B squared is the identity, because you're gonna have B times B, which is the identity, and also A squared is the identity. Now we continue as follows to conclude the proof. We conclude the proof. Since, for instance, since in every group inverses are unique, so since inverses are unique, since inverses in a group are unique, it means that AB is equal to BA, and thus G is abelian. Thus G is abelian. So since inverses are unique, because if ever AB times BA is the identity, it actually means that AB is equal to BA. Why? Why? I mean, there are, yes, I mean, we can show a little bit more steps, but obviously, since inverses are essentially unique, it means that AB is equal to BA. But also, we can actually be in a position to demonstrate this in a very, very meaningful way. Since inverses are unique, it means that this AB is equal to BA. Right, but now you really can have, because we want to show that G is abelian, so we want to show that this AB is equal to BA. We want to show that this AB is equal to BA. But I want to demonstrate something small. For example, if ever you have, if we claim that indeed E is equal to AB, BA, why? Well, because we've already said B times B is B squared, which is E, and that is E. This equation is sort of the power equation. It's the most powerful of equations we have. It's able to give us the result. So let us explore these things here. Right, let us explore these things here. Let us explore these things here. So in the end, then, if ever E is AB, BA, what else can we do here, mathematically speaking? Okay, because we're saying since inverses are unique, it means that the inverse of AB is BA. Simultaneously, we can write E is equal to AB. There's something I want to demonstrate here, some intermediate step. So we start with AB and we want to remove this BA, or we can remove this AB. Any one of those is okay. which one is worth removing. We can use the cancellation laws, for example, right? Using the cancellation laws and the notion of inverses. So you can write AB inverse E AB. I want to write here. Right, there's something I want to show. So now we can have the following. I want to show something very interesting here. Right, so we're good. So this would be AB inverse E. Like we can use AB inverse AB BA. So that now we have AB inverse E is equal to AB inverse AB inverse AB would give us what? Okay, yeah, but I mean we can do it like this, but there's more we can do even if we don't even use this inverses. Okay, let me change my mind. Okay, it's the same thing, but yeah, it's easier because this group is a group it's sort of idempotent. It has idempotent elements, that kind of thing. So we might not even decide to use the inverses because these elements of order 2. So we can do this, multiply by AB and multiply by AB and then have AB and then have BA like this. And yeah, we're done with this, okay, because it's shorter. Then at this point, what we have? AB times the identity is just AB. But AB, what is AB times AB? AB times AB is E. So which means that this is going to be E for these two, and then it's going to be BA like this. So which means that AB is equal to BA because of that. So indeed, that would be a more elegant way of showing that. And I'm thinking we can actually, it's okay, but we can include it as part of the proof. So that it's not some side working, but it is the most important part of the mechanics. So we can say, as part of the proof, we have and E is ABBA. Why is this ABBA equal to E? It's because B squared is E and also A squared is E. And this means that we can multiply AB E. And then we have AB, and we can group them like this. And then BA by associativity. So that AB times E is just AB. AB is E. E times BA. AB is BA. And the fact that AB is BA, and we can say hence G is abelian. You see, this is actually a very nice way to do it, but not only that this is sort of a nice way to do it, but it actually is obviously also, furthermore, it is anchored by the fact that since inverses are unique, so the sort of motion, the sort of motion from this step to this step, elaborations on the fact that since inverses are unique in every group, since inverses are unique, AB is BA. Anyhow, you still can do without this statement here. By just algebraic manipulations. I'm sure it's very easy, right, and clear. All right.
Yes, it's clear.
Okay, good. We move forward to the next question. Some of these you will participate so that you do not fall asleep. I'm going to give you some parts to participate so that you can share what you think because you're the only one on the line and you must always have a chance to learn. Let's take the next question. Here's a nice one. Okay, and they love this in your tests. They love these things in your tests. Okay, they are like small brain teasers. But let's look at this 33 because I was looking at the numbers that you sent me there. Let G be a group and suppose that AB, we suppose, so we actually suppose that AB all squared is A squared B squared for all G, and we need to prove that this means that G is abelian. All right. Okay, very easy. But now we have this little problem in front of us, and I'm looking at it. We're going to do it just now, of course. There are some parts where I'm going to give you a fair chance to partake because, yeah, all is well. All is very, very well. All is very, very well. Okay. Okay, we have this. We're not in a hurry. I'm sure that you are thinking about it, but it's very easy. The question is, how will you prove? What are we supposed to prove? From this, we need to prove that AG is equal to BA. But it is stemming from the fact that whenever you have AB all squared, it is the same as A squared B squared. Okay. This is awesome, like fine oil. Like fine oil. Like fine oil flowing down the beards of Aaron. Okay, never mind that. I'm just remembering some biblical teachings about the oil. Okay, now this is what we have. Okay, let's prove this together. Obviously, there are too many ways to prove this, but let us look at the proof. This is the proof. But we know that as part of the proof, we will say for all. For all AB in the group G, we have for all AB in the group G, we have that. Okay, let's write clearly. I want to write a very clear statement here. According to that one, we have that whenever we have AB, in other words, let's first do this. For all AB in the group, we have AB all squared is A squared B squared. What does this mean? This means that you actually can be able to write, because they said AB all squared is A squared B squared. So it is AB, AB, AA, BB. Okay. This looks like a ball game, but it's everything we need. It's everything we need. Because they just gave us AB all squared equals A squared B squared. But we can write it as AB, AB, and the A squared is AA, and the B squared is BB. Now, we have the following. Okay. Okay, y'all. Righty. Okay, we're good. Okay, we are continuing. Remember, you have a chance to reason sometimes when I pause, because I'm just pausing maybe to drink coffee. Can never mind that. Okay, right. I'm just pausing to just sip on a cup of coffee and see what we can do. Okay, now this is what we have. So we can do a nice thing. This is what you can do. A inverse, AB, A, okay, AB, AB, B inverse, A inverse, AA, BB, B inverse. So now we are able to see something, that the A inverse A is the identity, the B inverse is the identity, and this gives us exactly BA is A inverse A is the identity, leaving us with B inverse is the identity, and this means BA equals AB. Voila, we got it. And we say Eureka. And therefore, this is the result. We say this is the result. So when we then say, right, Eureka, so we have done this. So now this is exactly the proof that whenever you have AB all squared, which is equal to A squared B squared, then G is abelian because AB is equal to BA. And now you can then come and then say, if AB equals BA, and then you can say, hence, G is abelian. Hence, G is abelian. Right, I would imagine very, very easy and straightforward. I think that we need to take a short break for 15 minutes.
Okay.
Right, so now I'm going to give you a short break.
We can do 5 minutes. 5 minutes is okay.
Yeah, 5 minutes is okay. Yeah, you're right, 5 minutes. So now 5 minutes, meaning that according to my time, is like 11 past. So you're going to be right back at 16 past 7. Because, yeah, my time is 11 past 7. So in 5 minutes, 5 minutes. Thank you so much for noting that. You're pausing. Okay.
Hello.
Yes, welcome. Thank you so much for getting back. Okay, thank you so much. I just realized that these problems were not so many that at least you sent to me. Okay, I'm just want to show something now. So actually, my goodness, I was just looking during the break to see what problems exist. Now I was looking, I'm on WhatsApp now, and realized that we have done all the problems you sent, the list. In there, I was thinking there are going to be so many to take us, the kind of time. So okay,
The one that you wanted to do the other day.
yeah, I understand. Yeah. So now let me see. Right, because we have 1 full hour. Right. So in other words, you see, I'm on WhatsApp now, and I can see that on WhatsApp. I know this looks small, but now I can see that you said 8, 10, 11, 13, then 14, 16, 25, 28, 30, 31, and 33. From the textbook.
I can send you tutorial 3 maybe.
Yes, you have to draw 3.
Yes.
Okay, yeah, you can send that one. I think that it's fine. We've done 1 hour, so we can do 1 hour tomorrow. I mean, we have a long weekend. By and large,
Okay. No problem.
and yeah, I think that we have done 1 hour because I realized that 33 was the last one. I had not even realized it, but I can see that it's 30, 31, 33. And there are more we can do in the textbook anyway, because this is like the minimum, but we could like do more. So in other words, I will make a plan for our next discussion. I'm going to include more of the textbook problems because I was looking at a lot of the textbook exercises for this section. So right, but I'm going to load more so that we can discuss a lot more. But it's fine that we've done 1 hour, or in principle, I wish that we do much. Okay, but now if you have tab 3, we can include tab 3 in our next discussion. Okay, our next discussion is going to have other things. Okay, that's something very important.